It's a pleasure to introduce Myrto for our third and last lecture.
Thank you, Jasmine. Well, yeah, I'm a little bit overwhelmed by how much I want to cover, but we'll see. So let's see, where are we, right? We started with 4 problems. The first one was about solving equations of reach of unity. We forgot about it, but it's important that it existed because it allowed many other of the problems to come to life. Okay, the second was about when to map series to many common periodic problems. And yesterday we focused on the third, which is about when a dynamical pair of, remember, F is now for us a one-parameter family of degree D maps, where B is a cross-projective curve and A is a marked point or a rational function from B to P1. So when is this pair stable, meaning when it defines a normal sequence of functions by iteration. And we said that this happens exactly when an arithmetic quantity, the geometric canonical height of the point, vanishes, or exactly when the pair is isotrivial or preperiodic. Okay? And we used this to say something about the geometry of common preperiodic points. Remember, we had this at P, which is the pairs of parameters and points at which the point is preperiodic for f sub t and g sub t. Okay, so I'll have a second family, C. And we proved that it is Zariski dense in the whole space, because P1, if the pair F and G don't define an isotrivial pair. So I refer to this as a likely set, as I will be talking. And we stated a result that today we'll talk about. That said that the opposite is true if we square this set. P square this. You have now 2 common preperiodic points at the same parameter. Can only be Zariski dense in its total space, which now has dimension 3. When F and G are related in some extra way. But okay, what's the plan now? I want to talk about the proof of this, which will lead us to talk about problem 4, which, if you recall, was when does the wedge of the 2 invariant currents of F and G vanish? Problem 4 will lead us back to understanding the geometry of the set P. And in the end, if I get time, I want to give you kind of a bigger problem that contains all the 4 problems that we discussed this week. Okay. But that may be a lot, we'll see. Okay, first, Laura made an important point last time that I didn't prove what I wrote, right? In fact, I'm being vexed. I didn't write what I proved exactly, but I will today. This is important. So B, F, G are defined over Q bar. Not. And this is important because the proof, yeah, it's not complex, it's arithmetic. It's completely arithmetic, at least in this case. Well, not completely, sorry, it has complex. Okay, but, well, the proof, maybe I should say now, proves also a third equivalent statement about small points, since small points are in the title. Let's bring them here. All of them are equivalent to the essential minimum of the sum of heights. I'll write them in there. Being 0. Okay, what I write? If this is 0, it means X is periodic for Ft. This is 0 means X is periodic for Gt. And same for Y. So the zeros of these are the points in the p-square set, the unlikely set, I'll call it. But I don't need to have many pre-periodic points in the set. It suffices to have many small points with respect to this height function, and it still works out. This is an artifact of the method, okay? In general, these are known as Bogomolov problems. And I was talking yesterday in the air about some relative money-Mumford conjecture that has been recently proved by Gao and Habeger. In that case, we still don't know the Bogomolov version of the statement. But it's an accident of how the proof works here, and it's because the proof uses arithmetic equidistribution, a more fancy version that I will state today than the result we talked about in the first lecture. And yeah, that's all. Let me state. Oh yeah, right. It's throw away some varieties and count the minimum there. Okay, take the supremum over all the close-up varieties of the threefold of the finum of all the points in the complement of that subvariety.
Is it the same to say that? Is it the same to say that there is a sequence of points x n, y n?
A generic sequence.
Which is the riskiness and satisfies infimum 0.
Exactly. Yes.
I said we heard
Okay. Yes. Okay. Let me write that way because supremum infimum is anyway confusing. Equivalently, there exists Tn, Xn, Yn sequence of points in B cross P1 square that has no subsequence contained in a strict subvariety okay, of B cross P1 square, and right, and its height goes to 0. Now, how can I write all of that? Yeah, plus blah blah goes to 0. Small, but also it is generic. You don't want it to be living in a smaller space. Not even a little. Yeah. Thank you.
Can I just replace the first sentence by the riskiness diagonal?
Yeah, it just has to convert to generic point if you want. Oh, the risk dense? No, because then you may find subsequences living in smaller space, right? And then how can it equidistant?
Yes, but by a diagonal extraction, you can extract a generic sequence.
But then maybe that one's not having height.
If the generic sequence tends to 0, any extracted sequence will tend to 0. So, yeah. Yes, you can.
I'm more worried about bigger.
Why?
Okay, maybe. All right, whatever. Anyways, maybe we can keep this for the questions.
Well, in particular, yeah. Let's make it generic. I'm not worried about two potential limits being there. That's all. Okay. Theorem, what happens to this? Anyway, the point of this equidistribution is to understand the geometry of small points in families of endomorphisms. I'll write them, though, only for pre-periodic points and pretend that you can believe they work for small points as well. I will not write them all, okay? First, let me say it was proven, the result I write was proven by Johann Zank, but also the work of Kuhne and Gautier, Taflin, Vigny, and you can ask Thomas, he knows how to prove completely. And it's here. Okay. I'll write it in a more general form than we need, but it's good to have it in mind. So now I'll take a different base. I'll call it S, which will be a quasi-projective variety of any dimension. It doesn't need to be a curve, and it could even be a point. Okay? And what else will I take? I'll take P. Okay. Make a family of split maps over S. Okay, so P is given by F1, F2, Fn. All of these maps have degree D. To be honest, you don't have to. You can remove this one and do families of endomorphisms of Pn. Okay. Let me keep it here. Yes, it's my new way of writing P1. Yeah, because I want to erase the one later. It works without the one as well, whatever I'll say. Yeah, if it's just Pn. So this is P1 to the n product, and it works even if it's just Pn. Okay, there's a lot of things to set up. Right, now fix also X, a family of subvarieties, which is flat over S. Okay, this means it doesn't live in a fiber. Basically, we can pretend for all points in S, the fiber xt has the same dimension. I wrote X here. Yeah, this is supposed to be the generic fiber. Equidimensional fibers. Family of curves, family of the surfaces, and so on. Else, right, nothing else. Now we want to understand the geometry of pre-periodic points. So let T K X A K be a generic sequence in X bar be a generic sequence of P pre-periodic points. Again, I don't want this sequence to have a subsequence living in a smaller dimensional variety. Then, what is K? Suppose that P, S, X are defined over K. K, say some finite extension of Q. So Q if you want. Okay. Then the Galois orbit of, let's call this pair Zk, equidistribute to a measure in X that we can write as the fiber-wise green current of phi, which I haven't defined, but in the case of split maps, you can do that easily by taking the fiber-wise green current of the components and pulling it back in the various coordinates. This restricted on our family of subvarieties. This is now not a measure. So to make it a measure, to the dimension of X. Okay? But this also, this is now a measure. Okay? I wasted that up to the correct power. But, okay, the Galois orbits of the K, I will consider the discrete measure equally supported on each Galois conjugate of Zk. That will be a probability measure. So the limit has to be a probability measure. And this may not. So let's put down over here, over the total mass of this thing. Let's put it. Okay, but if I put that down there, then, yeah, you see why I left space here. I can't have it be 0 because it wouldn't make sense, right? So assume that this is not 0. Then this happens. Okay, we'll process it a little bit. Maybe first, do I need to write down what this means? Maybe it's 2. Any questions about it? Yes. Thank you. Okay. Maybe before I write the precise statement, it is precise. I think it's clear.
Sorry, sometimes in this generality, I'm a bit confused between like what's a dynamical plane versus a perimeter space.
Okay, total space here. So we are literally taking, I'll write it, 1 over the degree of Zk of the sum of overall the Galois conjugates of Zk, the discrete measures, and this converges to that measure weakly in X. So this works for every compactly supported continuous test function in X. Thank you. Okay, but still I don't expect to understand everything. Let's see what's going on here. First, yeah, K, I put it there on a second thought, because indeed, it doesn't necessarily have to be an extension of Q or Q. So I'll add in pink extra things to the statement. K, we can take it to be a number field or an one-dimensional function field. Okay. The example to keep in mind for our purposes would be Q bar of B or CB that we were talking about. Okay. But then, of course, this doesn't make sense the way it's written. But this is because it's not written in its full strength yet. If I wanted to do that, then I would have to, okay, say, then let V be a place of K. Right? And then write an analogous statement at every place of V. So far, I had only done that for the standard absolute value over Q, right? Of course, then I have to make sense of the objects that appear over here, right? What is this current? What's the wedge? This has been made sense, actually, first as a measure and then as a current by Semperlois and more recently Semperlois-Ducrot for even at non-Archimedean places. So I'll put fakely a V there to indicate it's a different thing. And then the conclusion still stays true, except with these extra V's. And yeah, many V's. And this object lives in a Berkovich nullification of our family of varieties. I'll put another V. Okay, just to keep in mind. There is more, and we'll use more of it. Maybe now I'll take it up and discuss examples of it.
A quick question. So script X is not projected, right?
No.
Necessarily. So you don't know the total mass of this thing there. It's not really controlled. Somehow.
It is controlled by a theorem. Yeah, it's a theorem. You need to control what happens in the degenerations. But Gautier, Thomas, and Gabriel Vigny have control of it in general. If you want, it's the same as trying to define Arakelov intersection theory over quasi-projective varieties. You have to define it. Okay, examples. Examples we have seen. Suppose I had only one map. Example 1, n equals 1. So I have one map F, and say S is a point. So it really, it's not a family, it's just a single map. Right? Then what happens? Well, I put this hatch there, but then this is supposed to contain the equidistribution of pre-periodic points from the first vector. Right, to the invariant measure. This limiting measure, mu px, is supposed to be just the invariant measure of f. But it contains even more. It says that this equidistribution works also at non-Archimedean places in some sense, and also even if this map is not defined over Q, but over Q adjoint T, a transcendental parameter function. Okay. Example 2 may be more interesting to see that condition happening. Take now again n equals 1. Take S to be V, our curve. Okay, and take X to be the graph of our marked point A. This is our notation, and F1, yeah. So F is from B, our family of maps. Okay, then what does this say? Then this theorem is talking about the pairs T, A sub T, such that A sub T is Ft pre-periodic. So I call them the pre-periodic parameters. Okay, we call that the bifurcation locus of the pair is contained in the closures of these parameters. And but to have this property, right? Then you need to have that measure will be non-zero, right? What is this measure in this case? The dimension of X is just 1, right? So this is T F hat with the graph of A. So it's exactly our stability for the pair kind of question coming up. And using the result we talked about, you can see that if the pair is not pre-periodic, which you know the distribution of the parameters, or it's not isotrivial, then all these pre-periodic parameters actually equidistribute to the bifurcation measure in this arithmetic sense, the Galois orbits. In complex senses, some equidistribution results were known earlier, but again, you can ask Charles and Dujardin, who will come next week, and Thomas. They have a lot of work on complex ways, things like that. Okay, no more examples. Example 3. Now let's focus. Example new. So we will need to use this theorem for the example of the likely set. Okay, the likely set. Remember, we know that there are infinitely many. There's a risky dense set of Tx in B cross P1, which are in common pre-periodic points for Ft and Ct. Okay, how do we even think about this language? We have to go back to how we went from lang to the common pre-periodic points question. It's all about which curves intersect the pre-periodic points of a split map a lot, right? So we need maybe to remember that this is just Txx in B cross diagonal curve in P1 cross P1 that is pre-periodic for Ft, Gt, the split map acting as Ft in the one coordinate and Gt in the other. Okay, so now what? Okay, so we know that there's a dense set of parameters here, right? What happens to them? How do they distribute? The theorem is going to tell us if we can prove that, say, okay, here we have two maps F and G, T, F, G square on B cross delta is non-zero. If this is true, then the Galois orbits of elements in P equidistribute to, I'll say, mu F G delta. Some measure. Okay. Maybe let's go back to this measure. You have to think about it in the diagonal, but maybe it's more convenient to rethink about it down on P1, meaning this condition here. Okay, you can make a computation and see that if you project this current down to B, it's the same as projecting down to B the wedge of the two invariant currents for F and G. So this is exactly our fourth problem, understanding whether it's zero or not. Okay, I'm using, if you haven't seen before, that the square of Tf and Tg is 0. Remember, it was defined with the Fubini studio form. So if you square that, it has to become 0. Okay, to do this computation. But it's easy. So our question becomes, right, when is this wedge zero? Okay, I'll ask you again now. Any cases where it's easy to see that it is zero? Right. If f is equal to g, or if these two things are the same, then it will be zero, right? Okay. Or maybe going back to that formulation, from there, it may be easier to see. This is a second reason. Oh, okay. I consider that the same reason as f equals to g. So, okay, the philosophy that we have seen is f equals to g has always to be considered with this Kronecker sense. F is related to g, meaning the diagonal, okay, is fg preperiodic. Or special, but here that's not the thing that happens. Okay, I'll say special. So yes, if the diagonal is special, then this is zero. How else it can become zero? Okay, if I square something that lives in one-dimensional space, I'll get zero. So if, in a magic way, not so magic. If I can manage to conjugate f and g simultaneously to make them defined over q bar, then I'll get zero. Meaning, if there is a trivial, I'll get zero. That's the second reason. Fg isotrivial. And we have seen then how the p distributes, right? It just lives in some lines. Can't satisfy such nice things. Okay. What about the converse? Is the converse true? And indeed, that will be the theorem. But maybe for you, how do you even think about this question? Like, how do you even think about this measure, this wedge? Right? What does it see? Okay. Maybe this guy, the F invariant current, puts in a family all the invariant measures for F, right? So it sees the Julia set of F sub t as t varies. And this one sees the Julia set of G sub t as t varies. And to imagine having something on their wedge would be when these Julia sets intersect at the same parameter. But also, we don't want them to always be the same, right? That won't be a good reason. And indeed, I mean, later you can make this precise and even more concrete. Right. Later, after the proof of the theorem, Laurent I proved that the support of this measure, or kind of support of this measure, mu p d delta, is, which we will refer to as the bifurcation locus of the pair of maps, is the closure of parameters of points that are rigid one repellers. I'll define now. You remember, similar to bifurcation locus. Yes. Okay. I put on the total space. Okay, what is this? These are pairs P naught, X naught of points such that X naught is pre-repelling, so pre-periodic to a repelling parameter for both FT naught and GT naught. And is rigid in the sense, and we can't follow this point holomorphically to a common preperiodic point of F and G. The entire family. That's the rigid part. Yeah, on a disk. Yes. Yeah, it's all over a curve anyway. So yeah, thanks. Yeah, we state this more generally for any base parameter. Then you have to change the number 1 to the dimension of the base. But I'm keeping this for here today. And maybe here to mention, this brings together and is following proofs of results of many people. And I'll write some names for this implication. It's mostly Bab Epstein, when they prove the density of Misirevet maps in the usual bifurcation measure, and then extended also by Berthelou. Okay, I write some names. Bianchi, Dupont, and Gautier, Vigny, and Gautier alone. Gautier alone also helps us for the other implication, along with Dujardin, whose idea we can follow for that one. I'll stop here, but because this is good to maybe try to picture what this measure is trying to do. But stop there, because we didn't have any way to figure out when one can find such rigid one repellers. So instead, we went back to prove this characterization that I'll state soon. We went back to the arithmetic approach. You have 10 minutes. We went back to the arithmetic approach. But to do that, right, we need to start thinking of our condition as an arithmetic condition, right? And currently, it's a vanishing of a measure. Well, we did that already in lecture 2 in some case for the bifurcation pair, right? Remember, we said how Gautier and Vigny have even proven that the total mass of this bifurcation locus is the geometric canonical height of the pair. That was in problem 3. In fact, their paper does more general things, and in particular, it also does the case that we're looking on right now. So TFG square B cross delta on B cross delta, its total mass is also the canonical height of the diagonal, which I defined, okay, only in the case of Q bar, but you can really do exactly the same. Now replacing the classical veil height with the veil height we defined over function. So in a way, we are trying to understand when this canonical height is 0. Theorem. MS. Canonical height. Geometric 0. If and only if. Okay. So this is the same as our condition. If and only if B cross delta is FG preperiodic or isotrivial. to be fair, we didn't use this result in the proof because kind of it's already embedded in the proof of Yuan-Zhang's theorem. So it was part of the theory anyway. But it's good to have it in mind. Okay. So now we have to prove this. And it reads pretty much exactly the same as the last result I wrote on day 1, which we did prove. So we'll try to copy that exact proof. But the first step in that proof was to find another way to understand when canonical heights are 0. And I had mentioned this fundamental inequality proven by Zhang, right? Here, we'll use the same inequality, but proven by Gubler in this setting of function field. So, put a second. Proof sketch. Everything is equivalent to essential minimum of the sum of these geometric heights zero. Now I'm lucky that I have restricted this talk to the diagonal. I have a couple of ways to proceed. I'll pick the one I think maybe easiest for you to believe. Okay, so we have a sequence that a generic sequence, an infinite non-repeating sequence that has height that's small with respect to f and with respect to g, right? What happens to the sequence? We saw they equidistribute. They equidistribute to the measure, or the invariant measures, and in fact, at all places. Okay. Places of which live on Berkovich analytifications, but Charles told us that the potential theory exists in these analytifications. Things work out very well. So you can write this also as the Laplacian of the escape rate of the lift, where you replace a classical absolute value with a v-adic absolute value coming from the places of this function field. And here also, it's a sketch. So the difference of these two escape rates is a harmonic function. It has to be constant. And you can sum them all, dot, dot, dot. Okay. I'm cheating a bit. Okay. These are not obvious things. Theory has been developed. And you can read Benedetta's book, yes, I love it, along with Becky Ramley's book on Berkovich space. And all the theories there. Okay, which then you can sum them over, remember, and you get that the geometric canonical height of X is, well, it differs from the geometric canonical height of G by a priori some constant that comes from all these constants over here. But because they have a common small sequence, that constant will have to be 0. So no constant. Okay. And now what? Well, now you know that this becomes 0 exactly when this becomes 0, right? So if you pick a 3-periodic point of f, I'll do it. Yes, then it will have G canonical height 0, which means it will either be periodic or G and itself will be in a trivial pair. We have done this argument, right? So we have two cases. Either we can find infinitely many common periodic points, or you can find many 3-periodic points of A of growing period that happen to make G and themselves isotrivial pairs. With interpolation, you get then that F and G as a pair are isotrivial. Blah, blah, blah. So we used implies with using problem 2 and problem 3, okay, that F is related to G or FG is trivial. We literally used problem 2 and its proof. And problem 3 fully. Any questions?
How do you define the geometric height of the diagonal?
Right. Remember, okay, you can define the Weyl height of a point in P1, right? You can then define the Weyl height of a point in Pn. Okay? So then if you have any variety in Pn, after you compute its tau form, you can take its coefficients, they give you a projective point, and you can take each projective height. That's how we did it. And then, well, you have now a Weyl height. You can iterate it with a map and take the limit of the height of the iterate normalized by d to the n. This is the cheating way that, actually in this case, Gubler had kind of done this way, but it was mostly Philippon that started this way of finding the height. It's not. Otherwise, you take actually intersection numbers, classical intersection numbers in correct models of the thing, and it's iterate, and you limit them, normalize. It's not safe to define the other way. We can talk after. So, okay, I say you do it like points. Have something in mind. And with this definition, actually, it helps because you can see why this equality may be true. We copy the proof we did for point, for f and a, the pair. You can see you need to take a limit from outside to inside.
Myrto, can you help me understand how this closure of the rigid one repellers relates to the Julia sets? I mean, like in the case when the Julia sets are both the full Riemann sphere or something like that. Like the Julia sets are always moving through each other.
Yeah, that's why that statement was vague, right? We were trying to imagine how it could possibly look, right? In the case of the Julia point, the elliptic curves, indeed, it's easy to find rigid repellers.
Yeah, but not that kind of.
Yeah, exactly. That intuition may not work exactly, or at least I also would have your problem. I also would have your problem. Maybe Laura wouldn't. I don't know. What do I want to say? Man?
It should be over all the parameters where the Julia sets intersect. Just logically speaking. It should be that.
Then it's probably supported in that case.
And then it would be-
But just knowing the Julia sets are moving through each other somehow doesn't give you these pre-repelling comments.
Posteriority it does.
Well,
So what does pre-repelling mean?
Yeah, it's pre-periodic to a repelling. So each iterate is a repelling. Thank you. Okay.
sorry, one more question. I mean, like if this has all been developed in all places, why can't you choose some other place for it to be repelling? Or it'll be repelling for some place.
Well, then you'd have to prove. So I said this theorem, right, relies on a lot of work of people using complex ingredients, motion of hyperbolic sets.
You also told me there's really hard to curl and
They developed the formal theory that can do the formal things, but not the dynamics of the dynamics of. Already Sal said it fails, like the stability statement fails, stable families. You have Julia sets that are the same everywhere. So I don't know. Yeah, lots of things to do. But it's a good question that I would assign to someone. I was glad I didn't have to do it. At some point I thought I probably will have to. Okay, but yes, thank you. Maybe going back, sometimes, yes, we already saw, sometimes we can find rigid repellers, for example, the lattice maps, then you still need to argue, but you can believe that there are many repelling points, all the periodic points are repelling. So you can believe you can build one repeller. And since this theorem works over any base dimension, even though I didn't state it, in some form, anyway, Laura and I managed to prove that the total space of the degree D maps times degree D maps is non-degenerate, leading back. I haven't even said anything. Okay, leading back to theorem. I'll say this. there's a uniform bound in general. NVD. Such that the FNG away from BD, for all pairs of maps away from BD, you have at most m common periodic points. Okay, and well, Laura may tell you that we can now describe proper Zariski clause set BD more explicitly, but I forgot completely to tell you how we were doing all of this. So we proved right here, we explained when this measure is non-zero for the diagonal, and I had said some equidistribution theory, right? How do we prove the unlikely intersection set is unlikely? Which, as we said, it would imply some statement like this for curves. Too small. I'll just say it in a few words because I don't have time and I won't say so much. This is, again, we have to use equidistribution twice. This idea of using equidistribution twice actually comes from Ulmo and his proof of the classical Bogomolov transaction for curves first in Jacobian. Anyway, so suppose that you have now a generic sequence of points xn, t, n, xn, xn, because it's in the diagonal, and then another diagonal that are pre-periodic for ftn, gtn, ftn, vtn. Right? Then you need to build two sequences of points that are pre-periodic with other maps and equidistribute. Well, there's a clear way to do it. Then you have Tn, Xn, Xn, Yn is pre-periodic for FG, F, and FGG. And so it has the potential to equidistribute to two measures as long as they are non-trivial, which they happen to be because at least in the cases that are not covered, that don't have zero canonical height. So if so you will assume this. It's a global assumption now, and well, it takes time to write down this measure. Let's write the maths. P1. So I'll take two projections. P1 from B times P1 cubed to B times P1 square, the first two coordinates, and P2, the last coordinate. So you get P1, PFG, and wedged with P2 star of TF from the first sequence, which is non-zero whenever this one is non-zero, exercise. And you get TG from the second sequence. Okay? And if both equidistribute, then the two heights are proportional, the two measures are proportional, some constant multiplier. And now, yes, maybe if you understand how these pullback wedges are defined, and you happen to find a paper by Besserella and Bertelut that explains things in more detail, then you see that this means that the slices of TF and of TG should be the same for almost all parameters tracked by this measure. Dot, dot, dot. Okay, and this is a nice measure. It has continuous potentials, it says. It does not charge points or lower dimensions of varieties in general. So you can at least find one transcendental parameter for which this is true, and that's enough, because then that parameter will give you, by Levin-Psitsky, a relation between F and G. At that parameter, so everywhere. Okay, for a trans parameter. There's many ways to do this argument. This is where the weekly special things appear, though, because this is happening for z square and tz square, even if it happens to be that the height of the diagonal for this example is non-zero. It's just that the corresponding measure is supported exactly when t is in the unit circle. Okay. No time to say what I wanted to say. Maybe I'll assign a reading to the class. So there is a conjecture that Laura and I formulated. Inspired by Pink's conjecture that I was talking about, and the result of Gauss-Habiger. Huh? So thank you. Yes. That in general characterizes when does a family of varieties X contains a Zariski dense set of P pre-periodic points. Going back to the setting of the equidistribution theory. Okay? So over any S quasi-projective parameter. So, I mean, the characterization is through a complex condition took here, which relates to the vanishing of a power of this invariant current. Okay, but this power is defined taking into account the dynamics of X and Phi, or it's as I didn't say anything, huh? Not one. Thank you. So RPX is the smallest relative dimension of an invariant, a Phi special subvariety Y that contains X. Okay. Now your exercise is to read the paper. It's called Distribution of Pre-periodic Points and Families of Maps, and explain why this conjecture implies all the problems we solved. 1, 2, 3, and 4. Oh, thank you. Yeah. Yes, the following are equivalent. Time. Ask me more now. It doesn't make sense.
Other questions? in this theorem, what's the VD? Is that like a symmetry though?
Ah, thank you, thank you. So at that point, we had no clue what it is. It just exists. Definitely, it should contain. It should contain all the maps. Okay. All the maps, all the pairs of maps that have same periodic points as a set, or same Julia set, or same invariant measure. It should contain that set. We didn't know. Now we know that we can prove that it is exactly the set, and more specifically, I'll write it. How did I write it? To be quick. Right, VD, but it's a finite union of subvarieties along which F is related with G, but in a family, or F and FG are both exceptional. Dot, 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 in which case you need to expand your notion of relation.
And then I'm sometimes confused in these theorems about like what's the parameter space and what's a dynamical space. Just the parameter space versions that say like when two subvarieties that have
Right, to prove this result,
inside of this statement.
right, the parameter space is built from here, right? The dynamical space is not clear, right? It's something like, pretend there's a universal map from Rati square acting on P1 square. The dynamical space would then be P1 square. If you want to prove it, you have to take powers of that, but that makes sense.
All right, well, I suggest we continue questions during lunchtime and we talk for a lecture. And